just to briefly recap, in the first lecture, we sort of derived Navier-Stokes equation, the incompressible version for Newtonian fluids, and we sort of discussed its symmetries and global conservation laws. We discussed energy budgets, which also sort of brought into focus the role of nonlinearity in both redistribution of energy across scales. And then completely away from the Navier-Stokes, we looked into the issue of how nonlinear deterministic systems can give rise to chaotic behavior, right? Because these are features that will show up in more complicated, in the more complicated problem of fully developed turbulence. So in the lecture yesterday, what we saw, we began with two experimental facts, as it were. And the first thing that we discussed was the fact that if we measure the velocity difference across 2 points separated by r, and take the square of it and average over various realizations, or average over x, or average over time, then experiments seem to suggest that that animal grows as r to the power 2/3, and a completely analogous result, which Ritik covered in his tutorial yesterday, how to show this, is if you look at the kinetic energy spectrum, which is the distribution of kinetic energy across scales, these two are completely compatible, and experiments seem to show that this is indeed the case. We also sort of realize that there's another experimental fact, as it were, which is unlike what we are used to in Newtonian mechanics, where as you switch off friction and everything else remains the same, you will not see any loss of energy. However, in turbulent flows, the analog of friction now is viscosity. And very surprisingly, you have this sort of phenomena of the dissipation rate going to a constant value as viscosity goes to 0. This, by the way, is known as the problem of anomalous dissipation or dissipative anomaly. And in some ways, it still remains an unsolved problem. Then we moved on to a simpler cascade picture, and we'll return to this today, which sort of puts all of these together, how sort of energy transfers from large to small scales, eventually to dissipation. And then we laid down the basic tenets of underlying the sort of underlying work of Kolmogorov, and showed that that naturally leads to the fact that if I take, instead of power 2, if I take any arbitrary power p, I get a scaling which goes as r to the power p by 3. Along with, which really is a consequence of this, but this can be proved directly from the Navier-Stokes, it's the only thing which can be sort of proved, is the fact that the third order exponent is strictly 1. So whatever theory that we are going to develop should obey at a minimum zeta 3 equal to 1, right? So once we did this, we could all have gone home happy that Kolmogorov has solved the problem for us, except we realize that when it comes to real experiments, you see these exponents have a form which is, so Kolmogorov gives me this. If I call these exponents beta p, let's say, then Kolmogorov would have given me the straight line with a slope of p by 3, but real experiments seem to show some deviation, significant deviation, except that it hits the p equal to 3 point exactly. And we were trying, and then I remember we sort of ended the last class showing certain results which are independent of the Navier-Stokes equation. So they really have nothing to do with Navier-Stokes equation, but they have to do with real analysis in the theory of sort of random functions, to show some of the additional constraints that taking the mth power of any random function would sort of tell you a little bit how these exponents should be ordered. In principle, they tell you that this thing has to be sort of shaped somewhat like this, and most significantly, just by assuming finite energy in your system, which is a reasonable thing to assume for a physicist, you end up showing that I cannot suddenly find an exponent which goes down. That higher order exponents have to be either equal to or greater than the exponent at a lower order, right? So this is where we are at. And today we will kind of devote ourselves to hard work in trying to understand how I can try to tinker with this picture to start getting exponents which seem to multi-scale as the business, as it's called. All right, but before we sort of play around with that, with this model and in the business of Navier-Stokes turbulence, let me give you a simpler model where I'm able to prove some of these things more exactly. And that simpler model is something which goes by the name of the Burger's equation, favorite equation of mine, in one dimension, right? So this equation, of course, has a very checkered history, and statistical physicists sort of know this in a different avatar, which is known as the Kardar-Parisi-Zhang equation. And this equation has applications in cosmology, applications in sort of directed growth, et cetera, which will not be the subject of today's lecture, but it might be a topic of 5 lectures at a later edition of the school by Sanjib and Abhishek, which is to understand the statmech of the Burger's equation. What I'll do is I'll pick and choose from the Burger's equation and try and see that some of this, especially this result, which is completely counterintuitive, can emerge, in our analysis. So what is the Burger's equation? So this is in 1D, so I don't have to worry about vectors. So as you can see, so far so good. This looks exactly what you had on the left-hand side of the Navier-Stokes, as long as I put vector signs. And on the right-hand side, all you have is either a dissipative term, so this is known as the viscous Burger's equation, or you can write the same with the zero viscosity. Right. So the viscous Burger's equation, we won't use it, but just to let you, just to sort of remind you that if I write this in terms of some function psi, which I don't care about, I can transform this equation in the new variable psi and write it down, and then take a further transformation with a new variable, which I call 2 nu log theta. So I'm coming from here. I make the following transform. We won't use this, but this is just to, I can't really begin with the Burger's equation and not talk about the Hopf-Kohl transformation. So this is known as the Hopf-Kohl transformation, which you may or may not use in the rest of your lives. And this reduces then in these variables to something that you know very well, to a heat equation. It's a good check to do this. Just make the substitutions, be slightly careful with how you take the derivatives once you make these substitutions. And when you do this, then you know how to solve the heat equation. You knew it last week, actually. And when you solve this equation, then you sort of turn the crank backwards. From theta, you can get to psi, and from psi, you get to u, and essentially, you have an explicit integral representation of u of x. All right. We are doing a transformation u psi theta. Yes. So this is just like the heat equation, right? So to the extent that it has a meaning in the form of a heat equation, it has a meaning here. Yes. But this is just a set of tricks for me to actually solve this equation, right? Formally. Right? So since we won't be covering this so much, there are a couple of nice review papers that you can read by Beck and Khanin, Physics Reports, I forget the year, 2007 or whatever. And there's a nice set of Lesuche lecture notes, which is slightly, which the same Beck. This is also an archive. Okay. All right. But there's a simpler approach to look at solutions of the Burger's equation. So let's sort of construct those solutions. So let's begin with the zero viscous case. So essentially, I have delta U plus U del X U equal to 0. Remember, in the first class, we are able, I mean, all of us know how to replace this with a full derivative. So all this means is this. All right. The partial derivative with time plus U del X is just the convective total derivative. So what that really means is, if I have an initial condition, so I'm plotting U of X versus X, and let's say my initial condition, and here I will mess up badly, but I managed somewhat. Let's say my initial condition is sine X. So what that means, the fact that, excuse me, the fact that dtu equal to 0, I can think about this sine X as being formed of these little balls are forming my sine X, right? All right. So given that dtu is equal to 0, in time, what this will mean is that each ball will move with its initial velocity. Is that clear to everyone? So for example, the guy that is here, this is equal to 0. After some time, it stays here. The chap which was here, after some time, dt would have moved here. The chap that's here would have moved here because it has the same velocity, and so on and so forth. So but you notice something very interesting. You notice that the velocity here to the left, to the right of x equal to pi will be smaller than the velocity to the left. So you immediately see that at some point you might have a problem. You might have a problem that's because the guy behind you is moving with a higher speed. This is in 1D, so you cannot overtake unless it's on Bangalore streets. So what you end up doing is this thing starts to fold. All right. But that cannot go on infinitely because then you're stuck. You are stuck with having multi-valued functions. All right. So another way to think about this is the following. Suppose these guys which I've labeled with pink, which is the solution at a slightly later time because all these beads are moving with the same velocity. If I look at it from here, then I can certainly say that at some time t, the position of this x will be what it was at time t ago plus u0a, which is the initial speed, right? Because my speed is not going to change, there's no viscosity, so all I'm doing is to say that distance is equal to time into velocity. So if you think about it, then you immediately sort of recognize that in some way, this is a map which is connecting an Eulerian coordinate to use, I mean, it really doesn't matter what I call it, but let me call it Eulerian, which is connecting an Eulerian coordinate with essentially a Lagrangian coordinate. By the way, in case y'all are in your head trying to translate this to the Navier-Stokes world, that translation fails. All right, so let's not do it. This is a model that I'm going to introduce to try and show you that some of this work you can sort of come up with more analytically. Now, if it's a map, all of us know that the map stops becoming invertible once the Jacobian of this map ceases to exist, right? So the Jacobian of this map will essentially be, if I take del x, del A equal to 0, let us assume that it happens at some time t star. So that essentially means that T star will be equal to minus 1 over. So what does it tell us? It tells us that this map stops being a map. The coordinate transformation stops being invertible as soon as you come to a time which is the negative inverse of the gradient of the initial velocity field. Now, my initial velocity field was sine x or sine a at t equal to 0, x and a are coincident, right? That's how I set up my little beads. So in particular, this guy has a whole range of values which goes from -1 to 0, right? Because the derivative of sine is cosine, which is bounded from -1 to +1, sorry. So which is the time that I will pick up? The time that I will pick up is the slowest of the time at which there's this first breakdown of the invertibility of the map, right? Is that clear? So, at different points, T star will have different values. It could have 1 million, 1 trillion, somewhere it could have 0.8, somewhere it could have, 22, somewhere it could have 5. I should be able to choose the smallest one in which this has happened, and also one which will be positive, of course. So essentially, T star, for all practical purposes, will essentially be the maximum of this, and I just take the modulus, right? So for sine x, for example, the derivative of sine x is cosine x. The maximum value of cosine x is +1, so T star will be 1. So you had some of this in the tutorial yesterday where you had seen, did you use sine x? Okay, where you had seen with sine x at t equal to 1, you start seeing the first shock. So what happens around t equal to 1 is that the solution sort of develops this sort of profile, and slightly after T star, and I'll leave that for you guys to work out, but let's say at reasonably short times after T star, the solution of the Burger's equation is just these two ramps connected with a discontinuity, right? So all of this you can sort of work around more formally, but this is not about the Burger's equation. I just wanted to give you a reasonable insight onto how to construct these. All right. So essentially what we have is, for the zero viscous case, the solution of the Burger's equation in a domain, let's say minus L to L, just for simplicity of calculation, will be x plus L over t, x minus L over t, where x here is, and it doesn't matter if I put that equal, right? And so just to redraw this better, you have something here, you have something here, u as a function of x, this is plus L, this point, let's say it's minus L, and you have a nice big shock sitting here, okay, at x equal to 0 from symmetry. So the jump in this guy, which I call delta U, would be nothing but 2L over T. That's because the value here is L over T, the value here is minus L over T, so the separation is 2L over T. Excellent. And now comes the surprising bit in the story. And the surprising bit in the story is the following. You can calculate the total kinetic energy. So I won't go through the calculation, but you can just take this integral from minus L to 0, put in this. You can take the other bit from 0 to plus L, put in that. And once the dust settles, what you will end up having is or in the sense of the delta U. Excellent. So that's my total kinetic energy in the system at time t. Now, this is quite surprising for the following reason. I am in a regime where there is no viscosity, all right? Because there was this formation, I think I avoided using the word, but I'll use it now. Because there's this formation of a shock, which relates to certain singularities in the problem that we can discuss after the lecture, if those of you are interested, you end up with a kinetic energy, which is an explicit function of time. And so you can calculate the dissipation. I'll use the same symbol as for Navier-Stokes, which is just going to be, you can calculate this derivative, and what you will find when the dust settles is this will be equal to, which is strictly positive. So this is a easy example of what we are seeing in the Navier-Stokes equation, that when there is no viscosity, there is still dissipation. It looks a bit out of a sci-fi movie, but if you have shocks, this is exactly how all of this pans out. Yes, exactly. But the important thing is the fact that it's a positive definite quantity. So we need to actually complete this story, because you see what we had written here was this goes to a constant as viscosity goes to 0, right? So the way to complete this cycle of argument is now to look at the solution of the viscous Burger's equation, take the limit of viscosity going to 0, and then to see that what you get there is exactly what you got in the viscosity equal to 0 limit. All right? So essentially, I can then construct this game for viscosity not equal to 0. All right? And there's a very nice, easy solution that you can write, which I'm not going to go through. It's a little long in the tooth, which is to look at the solution zoomed in around the shock where all the action seems to take place. And you can, those of you who have GNU plots ready and available, you can plot this function and see that it sort of looks exactly what you will see there, right? You need to play a little with the values of viscosity L and X that sets the length scale and the viscous scale in this problem, but let's not worry about the pedantic details. So what you can do now is you can calculate the energy dissipation, but now I can do it more formally, exactly how sort of we've done it for Navier-Stokes. So I can calculate the viscous solution. Let me put a little index X nu there just to signify that it's a viscous solution. And what you get is the following. I'll just write down the final results so that we save a little bit on time. So I will say this will just be del X U squared. Remember, that's how we wrote the capital omega in the first lecture. But this is a 1D variable. And this reduces to the following horrible expression. Very good. So this is at x comma t. To find the global dissipation, I need to integrate this guy. And when the dust settles, and then take the limit of nu going to 0. When I do that, what I find is the following. exactly the same result. All right, so you just expand out the sec hyperbolic to the power 4, or look up Wikipedia, one of the two, or do it on Mathematica. And the surprisingly elegant result that comes from this is that this solution converges to exactly what I've written up there. So in the Burger's equation, the energy dissipation, and the Burger's equation formally looks like the Navier-Stokes without the pressure term, etc. The energy dissipation for finite viscosity can be calculated exactly because I know how to write the solution of the Burger's equation. I can then take the limit of viscosity going to 0, and I see that the energy dissipation does not vanish. I get a number. All right, and that is what we have here. Then I take a different point of view, and I work with the solution of the inviscid Burger's equation. There is no viscosity. I calculate the dissipation rate. Contrary to our intuition, I again end up with a finite dissipation value, which is positive definite, and I find that the two converge when you take the limit of nu going to 0. This, by the way, in turbulence is one of the really major unsolved problems. We know that it's very likely that the Euler equation admits dissipative solutions. Many people in mathematics try to look for those dissipative solutions. And the hope is, remember I had shown roughly in turbulence, now back to turbulence, that if I look at the viscosity plot versus 1 over nu, then somehow data seems to suggest that it goes to a finite value. First to actually prove that it does go to a finite value. That's a absolutely important problem in turbulence, unsolved. And the second step would perhaps be that this finite value, the number that you have here and here, matches for the Euler equation. So this, in a nutshell, might be what you might call the problem of dissipative anomaly. In Burger's, this is solved, so no coconuts or prizes for actually solving this in Burger's. So this we are able to show, at least in the simpler model of the Burger's equation. So let me just take 2 more minutes to show why this also happens in the Burger's equation, so that you'll have a feeling that this is not all doom and gloom, and that you can actually, get exact solutions, as it were, and see these things falling in place before we again return back to the world of Navier-Stokes. Okay, so what do I need? I'll just keep that. By the way, although it's not super relevant to what we are doing, but just for your, if any of you are interested in looking at these problems, some of this picture changes when you have a stochastic noise in the system. Some of what I discussed will become quite interesting and more involved when you have noise, and it really depends on what sort of noise that you're using, etc. All right, so let's look at that picture. So what's the velocity field? Again, the velocity field u of x versus x looks somewhat like this. And remember, we need to calculate this angle. Well, the great thing is I don't have to worry about vectors in 1D. And I want to calculate what is delta u to the power p. So many of you would have done this problem or looked at this problem in the past, but let's do it again in an easy way. I'm a great believer in doing things in easy ways. All right. So let's take a pair of points, x and x plus r. You get some other colored chalks. So let's say this is my length scale that I'm going to look at, R. So I can take a pair of points. One is here, and the other is here. So what will the velocity difference between these 2 points go as? We have the exact solution, right? It's a ramp. So if I take points which are lying on one side of this ramp, so the velocity difference corresponding to those 2 points of this sort, maybe I can, so this is, let's say, 0.1 and 0.2. This is a pair of points, let's call it 1, 1. I can shift this and make another pair of points, call it points 2 and 2, all separated by R. And I'm going to just slide it along this axis, right? That's what I need to do, right? I need to calculate the average. I need to integrate it over space to define my angular brackets as last time. So all that I get from pairs of points which are of this sort is that delta U goes like R, right? It's on a ramp. Okay, clear? Now at some point, I will cross this bridge, right? So at some point with those same separation, I will get a bunch of points. Let's say I'll color them with this color. Let's say 3, 3, maybe 4, 4, etc., which are all separated by the same separation R, but it's straddling the shock in some sense, right? Now, if I look at this contribution of delta U from these set of points, then the contribution will be dominated by the fact that there's a big jump of delta U. It will not really depend on R anymore, right? All right, excellent. So now I'm going to go ahead and calculate this. So this is an integral on this guy, but I can do it just by arguing the case out and sort of trying to get this done quickly. And I also need to take, if you remember from last class, where R is small. It goes to 0 when the Reynolds goes to infinity, but R is essentially small. So now the question is, for such an isolated shock, what's the probability of you hitting this? What should that depend on? So most of the times with separation R, I'm beginning from here, right? And R is small, so I'm going like this. Most of the time, I will be on this ramp with a probability almost 1, right? But there'll be very few occasions when I'm going to hit this shock, all right? In principle, when R goes to 0, that probability will become 0, right? Well, when R goes to 0, I'm either looking at a pair of points very close to each other, like here and here, and immediately I go between here and here, right? So the probability as R goes to 0 of hitting that delta U jump will go to 0 in some sense. So it's reasonable to assume, but this you can work out more precisely, that the probability of picking up this contribution is just proportional to, let's say, R over L. Right? I mean, you can normalize with L, or it doesn't matter if you sort of normalize things before, but it goes as R. Here? Okay, huh? As I was about to say, I really don't care if I'm normalizing it. Yes, thank you. Okay, right? So now if I want to look at the pth power of this, so let me go back to white chalk. So this will be equal to, let's say, I'll just be a little careless and write equal to, will be the pth power coming from here plus the delta U to the power P, which comes from the fact that you have this animal. But this is decorated by a probability to honor Sanjib, which is R over 2L. All right. So zeta p, my exponent that I will find. So since R is small, when p is greater than 1, small number to the power greater than 1 will always lose out to r to the power 1, right? And when p is less than 1, then small number to the power less than 1 will always win over just something which goes as r. So what I will see clearly is that zeta p will be equal to p for 0 and equal to 1. I'm being a little flippant with my use of greater than equal to sign. Someone more rigorous will complain. All right. So if I calculate what we did for the Navier-Stokes, the exponent and this, if you just take the next logical step to what Ritik was teaching you all yesterday in the tutorial, and you calculate all of this from your numerical data, there will be viscous corrections, but it's mild. What you end up having are points which are like this, up to p equal to 1, and then they're all flat. So this, in some sense, is an extreme case of what we had seen for Navier-Stokes. All right? In the Navier-Stokes, it's curved. Here, it's, it's really something which begins to smell of what you would call biscaling. The fact that there are two scaling exponents, right? So we shall see, so the whole point of this exercise in some way was to tell you that you can look at really exactly solvable models, and there you can find out precisely a sort of rigorous proof of these two things which show up in real turbulence. Otherwise, Burgers doesn't have a lot to do with turbulence. All right, this was just a way to illustrate this. But I had also mentioned the word intermittency, so let me take half a second to point that out. You can ask what is intermittent about this Burgers solution? Why is the simple sort of scaling thing that should have come from here, what is intermittent in the Burgers solution, right? Where intermittency, we sort of showed very sort of spiky and smooth behavior in the dissipation field, et cetera, et cetera. Now, if you think about it, and you can actually go back and plot this function and convince yourself, but otherwise you can convince yourself by seeing that for a field of this kind, there seems to be some singular object which is going around in the shock, right? The rest of it are just like, nice smooth ramps. All right. So you can, so there is a singular zero-dimensional object sitting here connected by things which are dimension 1 objects. So you can also calculate the dissipation if you want to see it in that same picture. And if I plot epsilon with blue, then what you will essentially find are things which are nearly 0, and then there's a huge peak here, and then again things which are nearly 0. So here again, it's the intermittent nature or the spiky nature of the velocity field which really is at the heart of the fact that you have this biscaling or multi-scaling. And we will see a little later with some examples, I'll keep coming back, you will see that this also connects to the idea that you have more than one scaling exponent h. Right. You can use the same ideas that we did and see that this will correspond to, the fact that this will correspond to some h equal to 1 scaling and the other corresponds to h equal to 0. But we will see that slowly as we go along, but if you want, you can already start seeing it. Okay. Everything's clear, right? Very good. So those of you who are doing or doing your PhDs or master or whatever in most StatMech, KPZ, etc. like problems. Health warning, this was deterministic burgers without noise with completely deterministic initial conditions. So some of these ideas will not be directly relevant when you think about KPZ with noises. But this could be a starting point for you to think about life. Yes, sir. Yes. By? You can write it as del x of u squared, yes. In a conservative form, you mean? Yes, yes, yes. Good point. So everything is conserved till you get to T star in time. So then what happens is once the shock forms, these gradients start to diverge, right? You can't really define gradients. So if you want to look at conservation laws and you want to do integrals and integral by parts, that's what we had done previous class. Some of those operations are going to be no longer valid because the gradients are not going to be defined. So everything sort of goes into the shock, which acts like a black hole, if you like, and you dissipate everything there, and you really don't know because everything has diverged there. So this is sort of partly related to the Navier-Stokes question of is it singularities which are at the heart of dissipation, anomaly, etc. In Burgers, we know because Burgers has a real-time singularity for most generic sort of trigger. Let's say if you have initial conditions which are trigonometric polynomials. So this is the deeply sort of troubling part, right? That you've removed friction, but you can still dissipate. It doesn't, but it could make you stay awake at night and worry about the future of humankind. I hope it doesn't, but okay, great. So let's get back to turbulence. So that was a sort of digression to show with exact calculations the fact that these two seemingly exotic features, counterintuitive features, features that we wouldn't normally predict, can actually show up in similar models. So back to turbulence, and let us begin by slowly going through certain steps, beginning from here to understand how I can get to that result, or if I can. So the first step would be something where I'll play the following game. So remember, I had this cascade picture, right? L. I use the letter I or P, I cannot remember anymore. Injection. And then I had this scales R, which were much smaller than R, much larger than eta, where these guys were being broken up into smaller and smaller pieces, etc. And then eventually at scales eta, you lose all this energy by dissipation. This was the picture we had, and I think we had also derived using this picture and this sort of argument what is the exact value of eta as some nu cube over epsilon to the power 1/4 and things of that sort. Now this picture is sort of no good for us to break away from Kolmogorov. Remember, this picture gave us exactly the Kolmogorov laws. So what we can do is we can be a little creative, and here's a flux. So and in steady state, all of these are equal statistically I, pi, and epsilon. So now we can be a little creative. And there are historical reasons why people started being creative about this, but let's not get there immediately. And what we can do is the following. What we can do is at each of these stages, so this is, let's say, some nth generation of my cascade. When we did Kolmogorov, remember we did scale invariance and locality, right? I'm now going to break something. What I'm going to break is the fact that all of these have the same importance. So I have a sort of parent eddy, if you like, which has spawned several next generation eddies, but not all of them are going to be equally active. Some, like me, might turn out to be extremely lazy and they'll do nothing. All right. So what we do is we erase some of these eddies, or I'll color them pink. So let's say at any given generation, two of these guys don't contribute at all to the dynamic. So the energy from all of this sort of then splits and splits into this. All of them, if I sum over the volume of all of them, they would end up with the same volume, but some of these are completely inactive. So what we do is we say that at each generation, only a fraction beta. So here, for example, beta would be 1, 2, 3, 4, 5, 6, 2. So beta would be 2 over 6, 1/3. All right. Sorry, 4 over 6, I'm going the other way. 4 over 6, 2/3 would be the value of beta for this sort of cartoon. So only a fraction beta is active. Not surprisingly, what we are going to describe is called beta model. All right. And beta, of course, lies between 0 and 1. For beta equal to 1, we go back to our good old cascade picture of yesterday and recover everything that is Kolmogorov. So let us sit on the nth generation. And we know that at the nth generation, the fraction of active stuff, I'm using the word stuff for want of a better word and to avoid the word eddy, will be nothing but beta to the power n. Every time there's beta, then the next generation will be beta into beta, etc., etc., etc. Okay. Now, in the previous class, the other day, we had already seen that the way we set this up is that R is equal to sum an to the power L. So for example, if you're thinking of a simple binary tree, A is half, let's say. So capital L in the first generation gives rise to 2 structures. Each of them is half L. The next generation, it will be 1/4 L, 1/4 L, 1/4 L, 1/4 L, so on and so forth. But in principle, it's a free parameter. You can take A to be whatever you want. And from here, because I'll use this result, so let me write it down, N can be written as sum okay, so far so good. Need more notation. I'm calling the fraction phi, and I put a little label R to denote that this is at the Rth, at scale R, corresponding to the nth generation. All right? So now with a little bit of algebra, what you can do is I can first use this for n. So I can write beta as and now I can do another manipulation and write this. Always remember, if you have logs sitting in exponents, then it's very easy to switch certain orders. There are various ways you can think about it. You can take the log on both sides, so you'll end up with log phi equal to equal to this ratio by log beta, and you can sort of permutate them around. And what you end up having is this as R beta log A. And I will write this as 3 minus d. There's no good reason for the moment to write it as 3 minus d. I just feel like writing it as 3 minus, and no one can stop me. All right, but we'll see how we can start to think about 3 minus d as a way. All right, so 3 minus d, let me write it down. All right. So in general, the inspiration for this is the following, and we'll see where this comes from. So the inspiration from this is the fact that I'm trying to work on 3-dimensional turbulence. And the inspiration for this comes from the fact that there might be some other fractal dimension which has entered the game as I start erasing these things. Remember, we sort of discussed briefly while I was introducing the devil's staircase about a Cantor set, etc. So I begin with a line which is in 1D, and then I continuously erase stuff till I get into some other weird magical world of a fractal dimension. So this sort of thing is known as the fact that you have a difference between the what would be called the embedding dimension in which you exist and the actual dimension in which all the action is taking place. This, in general, if any of you are interested to read up about such things in the world of fractals, etc., this is known as codimension. For the moment, all I've done is some algebraic manipulations, nothing more. Right? I'm just trying to, I mean, it'll come out reasonably, hopefully, transparently at the end of this calculation, but I'm just, since I wrote 3 minus d, I think I owe it to my audience why I wrote 3 minus d, and you will see why this might start to make sense a little later. Okay, very good. Actually, we can think about this 3 minus d codimension idea. So let me do a little digression. Oh, there's plenty. Let me do the following digression. Let me take a 3-dimensional volume cube for simplicity. It really doesn't matter. Just to tell you a little bit about what a codimension is. So I'm in a 3D cube. So d is equal to 3. That's the embedding dimension. So suppose I have different objects here. I can put in this an object which has dimension 2, some surface, let's say. Different colors might probably help. Some 2-dimensional surface like this in this box. I can put in a curve in this box. Curve is dimension 1. This is dimension 2. Here, of course, I'm only talking about integer dimensions because it's a bit hard to draw things which are non-integer dimensions. Or I can even think about a point, which is going to be dimension 0. Now I ask you all the following question. Take a little ball, small ball, imagine, of radius r, all right? And I move this ball around this cube of dimension 3. So I take a small ball of radius r, and I move this ball in this volume, in this three-dimensional embedding space. All right. So how close where does the ball have to be if it touches the surface of dimension 2? So if I keep the ball here, it's not going to touch the surface of dimension 2, right? I need to lower the ball, and I need to keep the ball within a length r on either side of this surface, right? So to touch this surface which has dimension 2, the probability of that happening using roughly the same language, I'll just replace this with the word ball, would be r to the power 1, which is the same as r to the power p minus d, which for the surface happened to be 2, right? Now you can work this out, and you can then ask what's the probability that it will touch the curve, which is of dimension 1. That would mean that you have to construct a little cylinder around this curve. Sorry. And you'll probably draw it better than I do. A cylinder of radius r, and you will see that that will go as r squared, etc., which is the same as 3 minus d for a curve where d is 1. Okay, so you get the picture how one starts to think about codimensions. So let's get back to this. Okay. So we have constructed what this is. Anyway, so you will also notice from these definitions that for d to be positive implies that beta has to be less than greater than aq. That comes from the definition here. Right? That's a minor statement. So what this whole process essentially means that this transfer of energy from the large to the small scales through the flux essentially starts at, I've forgotten, the pink ones are the dead guys or the live ones? I've forgotten. It doesn't matter. Dead ones, okay? So this whole process accumulates on a set of objects. So let's call that set S, which are going to have dimensions capital D. Right? So in the old Kolmogorov picture that we did for the cascades the other day, where there were no pinks, that capital D would be 3. Right? Because I begin with three-dimensional space, everything is happening in three-dimensional space. I'm not going there and using my duster to erase out certain objects to make where this sort of waterfall of energy starts to accumulate. They're not going to, in the Kolmogorov picture of yesterday, they were accumulating on regular objects which were the same as the dimension of the embedding space. Whereas here, by design, I have ensured that there are enough obstructions, that there are only some randomly chosen fraction of guys which are alive. And if I continue this process, then this whole cascade is accumulating on some bizarre set which has some sort of dimension which is no longer going to be the three-dimensional object that it began with, but some other dimension, perhaps most likely fractal, which is going to be capital D. And I'm going to assign that stylized S that I wrote, of which I'm very proud of, as the set S of dimension D on which all of this is accumulated.
But these are for time being put in by
They're just parameters, and we will see in some cases how they will relate to each other. So I'll again, from this model, I'll again go back to Burgers and Kolmogorov and see that in those extreme cases so because Sanjib asked this, so Sanjib, you can immediately see that for Burgers, this will be 1, and this D will either be 0, which would be the zero-dimensional shock, or that D could be 1, which would be just a straight line. So I will do that just at the end of this process. Because we are still not out of the woods, because we still, remember, we still have to calculate this guy. I have to have d greater than 0, yeah. And both of them eventually will turn out to be harmless. It's just a free choice, and I'll show some choices that can make sense. Absolutely. Okay, so if I do this before we go to more algebra, consequences of such a model. So the consequence first is that I can still define my VR as I did in the previous class when there were no fractals, when capital D was 3 and the beta was 1, blah, blah, blah. But now I will be interpreting those same velocities as, in some sense, the typical, which I did earlier too, typical velocities, but only, I really should carry the chalks around, but only on active heads or active stuff, like. Oh no, sorry, pink is orange for the next few minutes. Okay, great. So, and these sort of eddies, as we saw, they fill that fraction pi r that we had written before. So the kinetic energy per unit mass, just to be clear, because we've set density equal to 1 in all of this, would really be the energy that we have, but we now have only a fraction phi r of things which are contributing to this story. I put in the phi r. Similarly, I can calculate the energy flux using similar arguments. And I have energy flux as before, which was VR cube over R, but now contributing only pi r fraction. But this is interesting, because if I actually put in my fraction, then I have pi r is equal to VR cube by R again. Kolmogorov, capital D would be 3, that term vanishes, and you recover what we had the previous day, right? But we know, remember, that this guy will be the same as epsilon, which in the previous class we had written it as V0, I think. V0 cube over L. And now it's just a simple matter for you guys to kind of invert this story and write VR as VL R over L 1/3 minus E minus P, which in particular implies I'll just take a minute for you all to absorb this before I sort of forcefully make you absorb it. Well, I should tell you that this sort of stems from a very beautiful paper by Nelkin, Fish, Sulem, etc., which works out. I mean, there are several other papers, but I'll refer to them at the end of these sections. So what do we see? So what we saw was the following. The minute I made my problem fractal, So remember, we ended last class somewhere when we were here by saying the fact that things seem to multiscale or not follow the simple scaling analysis seems to suggest that you could have more than one Hölder exponent. I didn't use the word Hölder probably. You will have more than one scaling exponent h. The symmetries of the Navier-Stokes allows you to have as many as you want in the inviscid limit. So Kolmogorov gave me h equal to 1/3, which did not agree with experiments, at least at larger, for large p, h 1/3 would have been just following this. And so Kolmogorov suggested that you might have a little variation in the number of scaling exponents h that there is to this problem. So to get there, the first thing that we did was we twisted the Kolmogorov picture, and we said that let's try and bump off a few of these eddies. Let's imagine things really cascade on sets which are non-integer dimensional, sets which are fractal. And we call that dimension D, and this was just a little algebra. It's not too complicated, right? I mean, one is able to follow that, and then one comes up with this sort of a relation. So when I use that, and I've done nothing beyond what we did in the last class, except I stuck in all these fractions, because now these fractions are not one, but this is something. And then I end up with the velocity scale going as, this was up to where we had yesterday, but now having introduced this fractal bit, I see a correction to the Kolmogorov picture. Yeah. Except it still seems to be a constant. So if I fix D, I'll get H to be one number, not a spread. We'll see when we come there. Yes, sir. Not the column, but there's a deviation from the Kolmogorov. Yes. Yes. We haven't got there yet. That's because you see, if you look at this carefully, for a given dimension, for a dimension D, this is still a constant. So this will again give you a straight line. Right? If I calculate the higher order exponents, we'll go through that. Okay, but what you're right in saying is the fact that I've introduced a fractal dimension, I've introduced the fact that this process of energy transfer is accumulating not in a three-dimensional space, which is the embedding dimension, but the fact that I have all these holes which are created, and so the effective dimension as you go downstream is no longer going to be d equal to 3, but some other d that I don't know, as as Sanjib was pointing out, that will depend on the free parameter that I've had in this problem. I end up with this, all right? One way to fix that d might be to compare it with experimental data, do a fit, and fix what d is in real turbulence. We'll get there slowly. But all I want you to appreciate is the fact that you can break from Kolmogorov. Actually, you can do a little better. Let me go through this. Okay, this is clear. So let me erase this. Let me keep that for the moment. So what we got was H is equal to 1/3, that's Kolmogorov, minus 3 minus D by 3, that's an outcome of our choosing fractality. And this leads to the fact that SP of R, which is defined there, but let me define it again for you. Something like this velocity scale will go as The stuff in orange is the new stuff which gets added just because of that prescription. And so zeta p will now be p by 3. That's the Kolmogorov with the correction of 3 minus d 1 minus p by 3. We still have a long way to go, by the way, to bend this curve. Because for any given d, that's also a simple function in P. That's going to be linear in P. But you notice two things. One, what Sanjib was preempting. Once the dust settles, you immediately see that if d is equal to 3 for self-consistency, so the picture of Kolmogorov or yesterday's model, this term drops out and you get back to the Kolmogorov result of p by 3. So at least the model is self-consistent. And then you also see something else, which I said, that you can cook up whatever fancy theory you want to explain this set of data, but zeta 3 has to be equal to 1. So when you put p equal to 3 there, you see this term vanishes, p equal to 3. So even within the beta model, zeta 3 is equal to 1. If you want, you can do a little, you can go a little further, those of you who survived the end of my lecture yesterday, and you can also calculate the Hölder inequality where I showed how the exponents have to be ordered, and you'll see it also satisfies that ordering. So far, so good. We've sort of come up with something which isn't perfect because I still have zeta p to be a straight line versus p, but we've moved away from Kolmogorov while ensuring that all the constraints that need to be satisfied are somewhat inbuilt in the system. Very good. So we'll come to that as the next stage. Yes, the ensemble won't help us so much, but we'll see what will help us. But you're on the right track. Okay. All right. So just to complete this picture, you remember, so what happens to this viscous scale? You remember in the last class, we had calculated this viscous scale by equating the eddy turnover time calculated at R equal to eta with the viscous diffusion time scale, which is what's going to happen below eta because that's viscosity dominated, and evaluating, doing, equating these two things gave us an explicit example of eta. So if we do this, then what we find for the beta model is that the dissipative scale goes with Reynolds as where H has been defined there. Okay. So a couple more remarks. The model before we close this. One is that D less than 2 implies H less than 0, which is a direct consequence of what I've written there. And D less than 0 implies EK is steeper. How should I write it steeper in words? The reason I'm mentioning this, it's quite opaque to most of you, is that the steepness of beyond k minus a third goes back to a very interesting result from the 70s, which has to do with realizability. And we'll see a little bit of this on Friday. All right. So the last thing that I can do is people actually fit the scaling exponent that I have written here for small values of p, and they find, well, within some things, a reasonable agreement up to some values of p. Of course, it's going to be a straight line, but if you allow me to do that brute force, just to check this. So these were things, calculations which were done many years ago. And what people see is that the best fit for small p, not large p, for small p at least, is obtained when d is equal to 2.8 or so. And this 2.8 is an interesting number. I don't know if Ritik had time to go through the multifactorial full, yeah, but you end up seeing this 2.8 like a ghost in many places when you look at effective dimension, right? So let me just summarize this section for you because it's a lot of stuff. So to summarize, the beta model is a model of the velocity field So this is still as monofractal as you would like, except now I have moved from d equal to 3 to d equal to 2.8. But I will still end up with straight lines for zeta p versus p. Okay. Questions? Tired? Hungry? Yes. Sorry.
Method.
So with 2.8, let's say, Sanjib, it probably would, let's say, do something like here, sort of this scatter, it's data fitting. So maybe up to here, the scatter isn't so bad. And if I didn't show you this result, you might say that the beta model with d equal to 2.8 is a better fit than d equal to 3. That's all. No, so I'm saying, okay, so yeah, so let me draw it. So this is the experimental data, right? No. So this is three-dimensional turbulence. Okay. Everything is three-dimensional. I've got wind tunnel data. Okay. P by 3 doesn't work. Now suppose you're in the 80s and I had data, let's say, up to here. Then I can say, if I take the beta model, because I've done the theory, and I say instead of p by 3, I'll plot this with d as my free parameter. It turns out that when I take d to be 2.8, maybe it's sort of, maybe it does something like this. And then in a lab, you're happy, oh, one is a little above, one is a little below. So this is probably a good mean fit. But we know that this cannot be true because we have enough data now to show that it's really not a straight line. It is a concave function. Yeah, that's exactly what his question was. So we'll modify it. This is the first step. So we'll eventually arrive at what's known as the Parisi-Frisch. So just to give the game away. So what we'll eventually try and develop is the fact that who on earth told me that the if I go into this world, I can equally well say, let's say this is the room. I'm just making a little cartoon. There's a cascade of energy which is happening here. So at this point X, there's this large L which is breaking down with a given D given beta. But equally well, I can come here and I can again have a large energy containing scale, which is again crumpling and breaking down. There's nothing which prevents me from saying that I'll have a different D here, which is what you and Sanjib, I'll have a different D here, I'll have a different D there. and corresponding to each of these Ds, I will have a different scaling exponent H. Okay, so that's where we will arrive at either tomorrow or today if you cancel lunch. so, so okay, so that's where we are at. So what we are essentially trying to understand is this is a good way to follow as a sort of conceptual way to see that introducing these ideas of fractal dimension, even in this monofractal picture, after I'm just choosing one value of D, gets me away from Kolmogorov, not in a completely satisfactory way, but at least at small p's, it gets closer. Point one. Point two is that it satisfies zeta 3 equal to 1, so such a model may not be totally useless. And point three is that it allows me to calculate the inequalities which we did yesterday, the Hölder inequalities on exponents for random functions. It also satisfies that. So at least we are on the right track and there is hope. Right? Because unlike Burgers, I can't do any of this directly from the Navier-Stokes equation. By any of this, I mean to get that guy and to show anomalous dissipation. So I have to take recourse to pictures. Okay. Any other questions? No? All right. Everything clear so far? I mean, sort of, you're with me? Yeah? No? Okay. Questions? All of you look completely devastated. So do you want to take a break? Then maybe we can begin from here in the next class. Maybe that might be a better idea, right? And you want to absorb things? Who said yeah? Huh? No, you're just seeing who'll say yes and then we'll make them stay back. Okay, so fine. So these are sort of, so you can worry about this. Maybe I'll start from here in the next class without rushing through this. Maybe I'll just go through this again tomorrow, just the basic ideas, and then take it from there. Okay, but if there are any questions, come over and we can discuss. Okay, Chutti.